Okay, so in this video, we will be discussing recursion, and we'll be discussing recursion through some concrete examples. Okay, so this will be more of a mathematical video than a theoretical one. So remember, in order to implement recursion, what we require is a stack data structure. Okay, so in order to implement recursion, we need a stack. Now, in order to trace out a recursive function, we have to use the stack data structure. An alternative approach is known as a tree method. We can also go for what is known as a tree method. Okay, so we'll be seeing both these techniques in this video. I'll be taking up examples and showing you how you can use both these methods to find the output of a recursive function. But before that, just keep one thing in mind. Whenever a recursive function is called, what is recursion? Recursion is the process by which a function calls itself. Now, whenever a recursive call is made, that function call is pushed onto the stack. And whenever a function is called, an activation record is created on the stack. Keep in mind, whenever a function is called, an activation record is created on the stack. Now, this activation record will give us an idea of the behavior of the function for a particular input. Now, what I'll do is I'll take up an example of a recursive function and trace out the output using both stack and tree method. Now, the question is, when would you use the stack method and when would you use the tree method? Remember, for small functions, you would go for the tree method because it is faster. But for larger functions, I would suggest that you go for the stack method. So let's take up an example. Okay, let's look at this example. We have been given a recursive function. How can I say that this is a recursive function? Look, this is a function whose name is a, and it takes an input n. Now, inside this function body, I can see there is a call to the function a itself. So a function a is calling itself a. That is why this function is called a recursive function. Now, we have been asked to find the output of the given function for n is equal to 3. Okay, so let's see how we can use the stack approach as well as the tree method to find the output. Now, before I proceed to show you the process of finding the output, just keep one thing in mind. This is the condition. Now, if n is greater than 0, you come inside the body of the if and you carry out certain computations. Now, here you can see that the function a is being called. So this is the function a. Inside the function a, I can see that function a itself is being called. So a function is calling itself. So this is known as recursion. That is fine. But this is known as the recursive call. This is the recursive call. Now, look at the position where the recursive call is placed. The recursive call is placed at the end. The recursive call is placed at the end, and such a function, such a recursive function, or such kind of recursion is known as a tail recursion. This is known as a tail recursion. This is known as a tail recursion. Why is it called tail recursion? It's called tail recursion because you can see that the recursive call is placed at the end. If the recursive call would be placed at the beginning of the function, it would be called head recursion. It would be called head recursion. We'll see examples of head recursion as well. Now, if the recursive call is placed anywhere other than the head or the tail, it is known as body recursion. It is known as body recursion. So these are the three kinds of recursion techniques. When the recursive call is placed at the end, like you can see here, it is known as tail recursion. When the recursive call is placed at the beginning, it is known as head recursion. And when the recursive call is placed anywhere other than the head or the tail, it is known as body recursion. So I hope this part is clear. Now let's proceed to find the output of this function, of this recursive function for n is equal to 3. Now what I'll do is I'll draw a stack. So this is my stack. Now I'm drawing my stack horizontally because I want to show you the entire output on a single page. Okay, if I draw it vertically, then what would happen is I would take up much more space, and it may happen that I may cover this entire page. So since I want all my computations to be placed at one position, that's why I'm showing you the stack horizontally. Okay, so my stack will be growing from left to right. My stack will be growing in this direction, from left to right. Okay, you don't have to show this in the examination. You don't have to show this. I'm writing this only for you to understand things better. Now what is the value of n? The value of n given to me is 3. So n here is 3. Now you come inside the function and you check, is 3 greater than 0? Yes. So you come inside the body, and what is being said? Printf %d n minus 1. So the current value of n is 3. So what would you print? You would print 3 minus 1, which is 2. So the output is first 2. Okay, and now a recursive call is being made, and it is being made on n minus 1. Current value of n is 3, so it's being made on a of 2. So when we made a call for a of 3, what happened? Because of this call to a of 3, this statement got executed. We got an output. So the printf statement got executed, and a call was made to a of 2. So a call was made to a of 2. Now what did I say at the beginning? I said that every time a recursive call is made, an activation record is pushed onto the stack. This is an activation record. See, a of 3, I have made an entry for a of 3. So this entire thing is an activation record. Okay, and remember, one thing you can do is, for your convenience, you can number each of these lines. So this is line number 1. I can consider the brace as a separate line. So this is line number 2, this is line number 3, line number 4, and line number 5, and line number 6. So for your convenience, you can number these lines so that you can trace out the stack even better. You can find the output in a better manner. So now you have to find a of 2. See, so a call is being made for a of 2. So now you will have to find a of 2. So you make an activation record inside the stack for a of 2. Now again, you go back up, you check, is n greater than 2? What is n now? 2. So is 2 greater than 0? Yes. So you come inside and you print. What do you print? 2 minus 1. So you print 1. You print 1. Now after you print 1, what do? You make a call to n minus 1. So what is the value of n? The value of n is 2. So you will have to make a call to 1 because it's n minus 1. Here this is the value of n. This is the value of n. Here also this 3 denoted the value of n. So you have to make a call to a of 1. Now when you make a call to a of 1, another activation record will be pushed onto the stack. So now you will have to see how a of 1 plays out. So again you check, is 1 greater than 0? Yes. So you come inside and you print. What do you print? You print n minus 1. What is the current value of n? The current value of n is 1. So what is n minus 1? N minus 1 is 0. So you print 0. You print 0 and then you make a call. What do you make a call to? You make a call to n minus 1. What is n? N is 1. So 1 minus 1 is 0. So you make a call to a of 0 and you had executed the printf statement. So this was also there. Now you make a call to a of 0. Now when you make a call to a of 0, an activation record will be created. Now you check, is this condition satisfied? No, this condition is not satisfied because 0 is not greater than 0. So you will not enter this body. You will not enter this body. You will come directly to line number 6. Now when you come to line number 6, it denotes the end of the function. That means this function call will return. Return to whom? This function call a of 0 will return to the function who called it. Who called a of 0? See, a of 1 made a call to a of 0. So a of 0 will return the control. See, it has no value to return. It has no value to return. It will simply return the control to a of 1. Why will it return the control to a of 1? Because a of 1 made a call to a of 0. That is why it returns the call to a of 1. Now what will happen? Now a of 1, where did it stop? If you remember, it stopped at 4. See, the call was made to A of 0 and that was at line number 4. So where should it continue its execution from? It should continue its execution from line number 5. And what does line number 5 denote? Line number 5 denotes the end of the if, which is followed by line number 6, which denotes the end of the function body. That means A of 1 will also return control. Return control to whom? Whoever called it. Who called A of 1? A of 2. If you see, A of 2 made a call to A of 1. So the control will be transferred to A of 2. Now if you look at this value, this is known as the instruction pointer. This is known as the instruction pointer. Now this instruction pointer keeps track of the next instruction to execute. That means A of 1 made a call to A of 0. As a result, the control was transferred to A of 0. Now once A of 0 returns the control back to A of 1, where should A of 1 continue its execution from? A of 1 should continue its execution from line number 5, which is given by the instruction pointer. So as a result, I can see that line number 5 denotes the end of the if, which further denotes the end of the function. Now A of 1 returns control to A of 2 because A of 2 made a call to A of 1. Now A of 2, on receiving the control back from A of 1, will look at its instruction pointer, which was line number 5 again. As a result, it denotes the end of the function. See, it denotes the end of the if body, which further denotes the end of the function. As a result, A of 2 will now return control to A of 3. Why will it return control to A of 3? Because A of 3 made a call to A of 2. And now A of 2 will look at its instruction pointer, which is again 5, and will finally return control to whoever called it. So it's safe to assume that it was the main method. It was the main method which made a call to A of 3. And now A of 3 returns the control to main, and the final output that you get is 210. So this is how you would trace out a recursion or a recursive function using the stack method. Now, what we'll do is we'll use the tree method to see how we can trace out the stack, or how we can trace out the recursive function. So let's see how we can do that. Okay, now let's see how we can trace out the same function using a tree. So what do we have to find? We have to find A of 3. We have to find A of 3. Now, to find A of 3, what are we doing? We are checking if 3 is greater than 0. Yes, it is. So it comes inside, and now it has to execute these two statements. It has to execute a printf, and it has to make a recursive call. See, for n equal to 3, this condition is satisfied because 3 is greater than 0. Now it has to execute these two statements, right? So for A of 3, you have a printf of n-1, that is 2, and a call to A of 2. As you can see, 3 minus 1 is 2. So a call to A of 2. Now what will happen? Now this is a recursive call. So A of 2 would again check this condition. Is 2 greater than 0? Yes. So you come inside and you have to execute a printf statement and make a recursive call. So A of 2 will also execute a printf statement, which is n-1. So 2 minus 1 is 1, and it has to make a recursive call, and a recursive call to n-1. So it will make a recursive call to A of 1. Further, you will check for A of 1, is 1 greater than 0? Yes. So you come inside and you print. What do you print? 1 minus 1, which is 0. So now you will have to, for A of 1, again, you will have to execute a printf statement, which is n-1. So if n is 1, 1 minus 1 is 0. And you will have to make a call to A of 0. Now, when you make a call to A of 0, you can see that the condition is not satisfied because 0 is not greater than 0. As a result, you stop your tree construction at this point. Whenever the condition is violated, you have nothing more to check. As a result, you stop the process. Now, to find the output, what would you do? You would trace out this tree. You would trace out this tree top down, left to right. So you will start from the root. So I start from the root. Now I have found a printf statement, printf 2. So I will be printing out. So I'll be printing out 2. Now top down, I have to completely traverse this. So I'll go up and I can see that there is a call to a of 2. So I'll go down and I can see a printf statement. So I'll print 1. Again, I'll cover the breadth, and again I find a printf 0. So I'll print 0. And then again I'll cover the breadth. So this is a of 0. Now a of 0, so when I'm going back, it's like a of 0, like we saw here, a of 0 was returning control to a of 1. So here when I'm going back, a of 0 is returning the control to a of 1. Similarly, a of 1 is returning the control to a of 2, like you saw here. So a of 1 is returning the control to a of 2. And then a of 2 is finally returning the control to a of 3. And that brings an end to the entire execution. And what is the output? The output is 210, which was the same in case of your stack. So as you saw that the tree method is a lot faster than the stack method. However, for larger programs, the stack method is preferred. The tree method will then prove to be inconvenient. When you have a number of function calls to make, the tree method will prove to be inconvenient because the size of the tree will grow exponentially, and then it would be difficult to keep track of the proceedings. Now, one thing you can see is from the tree method, what you can find is how many function calls are being made. So you can see for a equal to 3, how many function calls are being made? See, there is one function call to a of 2. There is a function call to a of 1. There is also a function call to a of 0. Now the question is, how many function calls? What is the total number of function calls that is being made? So you can clearly see that. So as I was saying, you can clearly see that total number of function calls being made are, see, 1, 2, 3. And we have to take the original function call because some function must have made a call to a of 3. Let's say I have written somewhere a main method, and there at some point I made a call to a of 3, which led to this entire computation. That means I have to take into consideration the function call to a of 3 as well as the function call to a of 2, a of 1 and a of 0. So a total of 4 function calls or 4 function invocations were made. 4 function invocations were made. Now from this we can conclude that for this recursive function that we saw here, if n is equal to, or let's say for n, for a particular value of n, or let's say if n is equal to 3, I had to make 4 function invocations. So if n is equal to 4, you can verify that we have to make 5 function invocations. Similarly, if I generalize this for n equal to k, I have to make k plus 1 invocations. I have to make k plus 1 function invocations, and it clearly denotes that depending on the value of n, we have to make a certain number of function invocations. So for n, for a particular value of n, we have to make n plus 1 invocations. So for a particular value of n, we have to make n plus 1 invocations. So I hope this is understood. So this was an in-depth example on how to trace out a recursive function. Now what I'll do is I'll take up one more example. So let's see how things are done.